Okay, so this is the revision for today. This is chapter 3, continuity equation, conservation of mass. All right. So what I will talk to you about is based on what we learned in class. So I want you guys to help me. If you have any question, please do ask me directly during my presentation here. You can stop me anytime. If you want to ask me anything about the assignment, anything that I can answer at this moment, I can answer. All right. Okay, chapter 3 over here, the basic for chapter 3, number 1, is on continuity equation or conservation of mass. This one is a basic because each time we do a study on chapter 3, conservation of mass or the continuity equation, the related equation towards it, okay, will be the one that we are using. So the basic part that you need to know is number 1, Q, volume flow rate, okay. And the equation is A multiplied by V, right? And A is the area, V is the velocity. However, you need to remember it is actually equals to V over T also, which is volume over time. Because the unit for this is meter cube per second. So there are a few things that you need to remember. 1 meter cube is equivalent to 1000 meter. All right. And usually for our study, we'll use meter cube per second because this is the SI unit, meter and second. Right. The second part is the mass flow rate. Okay. So mass flow rate, m dot over here, okay, is equal to rho AV. We add density in the calculation, multiplication of density, and it is equivalent to AV is equivalent to Q based on the definition above. So it becomes rho Q. Usually you'll use it when you are dealing with linear momentum, right? And it is actually equivalent to mass divided by time. Hence the unit for this particular part will be kilogram per second. And the last one would be weight flow rate. Okay, W dot weight flow rate. It is rho G AV, which is rho G. Okay, sometimes in the calculation it becomes lambda. You can just use the lambda given, gamma given, which is the sorry, I heard somebody coming in. Okay, so it is equal to rho G, okay. This is what we call as specific weight. Alright, so rho GAV 9.81 meter per second square. For G, AV is Q. It is also equal to weight divided by time because the unit over here is Newton per second. Weight can also be mass times G, right? So mass over here multiplied by G becomes weight, and then weight divided by time will be the weight flow rate. Okay. So for any questions regarding continuity equation or conservation of mass, all right. So usually the part where you need to remember is this part over here where we call this as continuity. Continuity means that whatever comes in on one side will come out to the other side based on the direction of flow, meaning we don't have any losses, we don't have any way of the liquid to come out from the system. So over here, we assume there are no losses. Okay. Oh, sorry, no losses in the system. So because of that, we will assume anything that comes in should come out. Right. So that's how we deal with continuity equation in pipe. I know this is not something that is actually happen in daily life, but usually for the purpose of study, we do this. If not, you need to take care of friction and everything else. That one will be a study that you learn in flow in pipe. Okay, chapter 4. Right, so these are the equation. Mass flow rate 1 should equal to mass flow rate 2. Weight flow rate 1 should be equal to weight flow rate 2. Q1 equals to Q2. So the very basic ones, okay, is Q1 equals to Q2. We use this a lot, which is it becomes A1 V1 equals to A2 V2. So based on this, you would know that this equation is used to usually to find V. All right. If you have area, you have velocity on the other part, you use this to find V for the other ones. Okay. For example, you have area for point 1, you have velocity for point 1. So point 2, you only have area. So you'll be able to find V by using this. Okay. And the last one for continuity and conservation of mass, this is what happened when you have separation. Okay. Okay, so what happened here, flow is coming into the system and then it separates into two parts, the top part and the bottom part. All right, and then it continues to flow back into one pipe at the end. All right, so what we are telling you right now is now we have one flow separated into two flows and then gets back into a single pipe here at the end. So the equation for this should be QA equals to Q1 plus Q2, all right, and equals to QB, right? If the area for both of them are the same, the possibility of the velocity to be the same is really high, okay, for Q1 and Q2. But it depends. So this part over here, it depends on the area or the velocity inside the pipe. All right, any question on this part?
No, sir.
No, okay.
No, sir.
Sorry, today is quite basic, but I'm doing this so that I can help you guys answering question for your assignment. Okay, the next part will be Bernoulli equation. So this is also called as conservation of energy. Right, so conservation of energy, the basic will be this equation here. So hopefully you will remember P1 over rho g Z1 V1 square over 2g equals to P2 over rho g plus Z2 plus V2 square over 2g, right? Usually we call the results for this in terms of heat. Heat, why? Because the number that you will get will have a unit of meter for each one of this. Okay, for example, P1 over rho g over here, the unit for this should be in meter. Z1 should be in meter. And the whole V1 square over 2g over here, the unit that you will get will be in meter. So that's why we call P1 over rho g as pressure head, because pressure is the main criteria here. Z1 is called elevation head because elevation here, Z1 is the main criteria. The last one is velocity head. It doesn't matter V1 or V2 over here because velocity is the main criteria here. Meaning, when you do your calculation, this will be the biggest impact for this particular part. So we call pressure head, elevation head, and velocity head. When we add everything together, it is called as total head. Okay. The purpose of having this total head is to find out what is the amount of pressure at that particular location in terms of meter. Okay, why is it head? Okay, remember the equation for pressure, P gauge, is equal to rho times G times H. Instead of multiplying with the rho G, we pull out the rho G so that we play around with H over here. The higher the H, the bigger the pressure because rho G is just multiplication. Okay. For example, you have the head to be 10 meter, combination of all head on 0.1. So it's just 1000, for example, water, multiplied by 9.81, multiplied by 10 meter. Right? In case we want to study about, for example, H is below 10 meter, so 5 meter, so the pressure will be lower than the pressure of 10 meter. Okay, so the reason why we are using this so that we don't have the hassle to calculate the rho and to multiply the G. Okay, right, so that will be the first one, okay, for Bernoulli equation. The second one, Bernoulli equation in terms of heat. All right, this one is a way for us to change from Bernoulli equation in terms of heat into Bernoulli equation in terms of pressure. Okay, how do you do that? Remember just now we leave out rho g. Now I'll multiply Bernoulli equation in terms of heat with rho g or gamma over here. Okay, so what happened? You'll get the Bernoulli equation in terms of pressure. So where is it? Here, this is the equation. P1, because rho g divided by rho g will be 1. So P1 plus rho g Z1 plus rho V1 square over 2 equals to P2 plus rho g Z2 plus rho V2 square over 2. So both of them should have the same equation. And right now, for each one of this, the pressure that we get is equal to a unit of Pascal. Okay. All right. So this one, it means that you already get the pressure in terms of Pascal. All right. Okay, the next one is, if you check from here, these are the 4 conditions that you need to remember each time we do Bernoulli equation. Why? Because we want to cancel out few things in the Bernoulli equation to minimize. So the function of this condition is to minimize calculation. Okay, and also to minimize number of unknowns. Remember, this is only one equation. So when we have one equation, we can only have one unknowns, right? It's hard for us to have 2 unknowns. We don't have a way for us to solve the question. Okay. Any question up until now?
I think no.
No, right. So
No,
not
sir.
yet. Okay, so let's go and find out the idea for these 4 conditions. Okay, so the 4 conditions that we have, number 1, if you have a reservoir or a tank, okay, the pressure exposed to atmosphere, it doesn't matter here at the reservoir or the tank, as long as it's exposed to atmosphere, or at the end of the pipe here where it hits the atmosphere, is equal to 0. Remember, some of you might get confused. Okay, it's not because of it's at the surface of the liquid in this reservoir it becomes 0. No, P equals to 0 when it hits atmosphere. The reason for this is the study in chapter 3 is based on P gauge. Okay, meaning we study on P gauge, we don't add P absolute. Because of that, P is equal to 0. The only time you have to use P absolute is when we have to deal with an open manometer, YouTube manometer. For example, a question from chapter 2. Okay, so when we have an open manometer, so usually we'll deal with P absolute. And manometer as a whole deals with P absolute. However, for other calculations, meter, normally we will deal with P gauge, right? Number 2, in terms of reservoir and tank also, V at the surface of a liquid in a tank or reservoir should be equal to 0, right? Here, V over here, at the surface of the liquid inside a reservoir or tank should equal to 0. Why? Because we consider the movement of water over here is really slow, going up and down or flowing from side to side. So we decided to go for V surface equals to 0. All right, this is coming from the textbook that we have for our class, and different textbook also provided it to become 0. Okay. And number 3 over here, if you have 2 pipes with the same area, okay, the velocity VA should be equal to VB. Why? Because we are using Q1, QA equals to QB. So AAVA equals to AB VB. So if both A's are the same, so VA and VB should be the same, right? And the last one, if you have the same elevation, Okay, it doesn't matter how the shape of the pipe is, but if the point of study is A and B, the same elevation, ZA equals to ZB will be there in the question, and we can cancel out in the Bernoulli equation. Alright, and at the end, if you are talking about Bernoulli equation, okay, one thing that you need to remember is, right, if continuity equation is lack of values, for example, especially in terms of velocity, okay, for example, V1 and V2 are unknowns, okay, both of them unknowns, right, in a question, and you don't have a way for you to study in terms of continuity because no flow rate is given to you. So we can do a replacement method, which is very important, which is how we replace whatever that we have inside the equation, because we have a relationship for V, so we can replace V1 with V2. So that instead of having just instead of having two unknowns, we can change it so that it becomes only one unknown. Then when you solve for V1, for example, if you solve for V2, you replace this. For example, you know the area, you should be able to find out what is V1 and to find out what is volume flow rate. So this one is useful in a times where sometimes the question for Bernoulli equation will have V as the unknown for both of them, and we don't have any volume flow rate to help you guys to find the velocity. Okay?
Okay, sir.
All right. Is it okay what I'm doing today? Because I'm doing this to help you guys for your assignment.
Yes, sir.
Yes.
Okay, okay.
Okay. All right. Okay, so this is the Bernoulli equation. Applications, right? We have multiple application. For me to teach you guys everything is hard because the design of the question is different. So please go and find out examination papers from the past. I could not give you everything, but please find it from EQPS. From there, you will discover that we have multiple questions regarding the Bernoulli equation applications. Okay, different shape, different configuration. So hopefully by doing a lot of them, you'll get the idea when to cancel out things from here and there. All right. So the first one is Bernoulli equation here in terms of this picture. So you can see we have two parts. So this part is called Venturi meter. Okay, the one on the left, right? So left side. This one is the right side. Okay, the one on the right side is called manometer. Okay, the function of venturimeter is to provide us a way to understand what is the difference between point A and point B. In terms of area here is correct. In terms of velocity, in terms of elevation, and in terms of pressure. So we use manometer over here to find out the delta P, which is the pressure difference between point A and point B. So each time you have this calculation, remember the Venturi tube will be related to Bernoulli equation. Manometer will be related to delta P. So over here, what you will have is the same Bernoulli equation here. All right, V1 over rho G plus V1 up until the end. So what we do is basically if you have a question like this, we have Venturi tube, we have manometer, we rearrange based on the picture and find out what is PA minus PB, which is the delta P. For number one over here, your Venturi meter. Sorry, Venturi tube. Okay, so ZB, ZA you can cancel out depending on the question. Whatever that will cancel out, can cancel out, right? And the VB over VA over here should be coming from your continuity equation, right? The second part is for manometer here, okay, you do the same thing. Find the pressure difference. For example, here is PA minus PB. Try and rearrange your equation for manometer so that it solve your PA minus PB. So for example here, we use the example that we have here, H1, H2, H3. So you'll get PB equals to PA plus rho water G H1, this part, okay, minus rho manometer. So we assume this is manometer. This is water assumption, right? So we have H1 done, and then H2 minus, okay, and then H3 over here also minus, because we start from A going to B, coming down is positive, going up is negative. So at the end, if you rearrange the equation from here, rearrange. Why? Because you want to change from PB equals to PA to PA minus PB. So everything on this side should move to the other side. So it becomes the other way around. Minus rho W plus rho M plus rho W. So at the end, what you do is we compare both PA minus PB for Venturi tube and PA minus PB for manometer. So then you can solve the one unknown in the question. Right? A normal venturimeter question will be like this. Okay. Sometimes you will see in different shape. Sometimes you will see it in this shape. Okay. Sideways. All right. But still, even though it is sideways, the idea is still the same. We want to find out what is the velocity inside the system. So even though it is sideways, the idea is still the same. We are trying to find out the velocity or pressure or elevation. It depends on the question. Okay, sorry. All right, like this, for example. Okay, so we may have the flow coming in like this, coming out like that. So this is point A, this is point B. The different thing about this is the manometer is down here. Okay, and for this part, you can see A and B should be the same elevation. So you can cancel out ZB and ZA. This one, they have different elevation for the one that we did just now. So we cannot do that. Right. The next question should be something called as orifice. Okay, so orifice over here means that we have an opening in a tank or a pipe. Okay, we call that as orifice. Okay, for example, here we have a tank filled with water. Okay, and water flows from point 1 to point 2. Here we have a tank, for example, it goes from point 1 to point 2 to point 3 over here. Okay, so for example, for question number, this question, flow goes from top to the bottom due to gravity. So we have, as usual, the Bernoulli equation written like this. And then we cancel out accordingly. For this one, for example, because point 1, the pressure is at the surface. So this one equals to 0. Z1 should be having a number here. V1 also equals to 0. This is based on the 4 conditions that we have. P2 equals to 0 because here, right? And then Z2 and then V2 square over 2G, right? So we might be, maybe the question asks us what is the H, maybe the question asks us what is the V. So what you need to do is just use whatever numbers that we have in the question, fill up this equation. So you can see over here, even though the Bernoulli equation consists of 6 items, which is 3 on the left, 3 on the right. However, if you cancel out a lot of it, you can end up with this equation at the end. Okay. Right, the next one is if you have a tank and then you have a pipe coming up, remember the flow of water coming out from the system should have a certain velocity. And if you have a water coming out and then it splash down again, so that will be the maximum flow of water. Okay, so after that the water will come down again, right? So at point 1, remember we have V1 equals to 0, P1 equals to 0 here for point 1. Okay, and then for point 2, we have V2 equals to 0, this point. Pressure should also equals to 0. Okay, let me do this. Okay, for here, V2 equals to 0. P2 is also equals to 0. Why? Because emitting the atmosphere. Alright, and then here you will have 3 over here. Number 3, P3 is equal to 0. V3 is also equal to 0. Why? Because this is at the maximum water flow rate, where after that the flow will come down. So that's a question. I think one of the question inside your assignment almost looks like this. So please do, if you have 3 points over here, okay, please do 2 different Bernoulli equation if you want to solve any question, right? If the question can be solved using continuity, you can just use continuity. If the question cannot be solved with a continuity equation only, so you need to find out in terms of Bernoulli. Maybe Bernoulli between point 1 and point 2, and then point 2 and point 3, or you can do a Bernoulli between point 1 and point 3. Okay. Any question just now?
Yes, sir.
No, eh?
I think no.
Alright. Okay, let me take another attendance for today because 2 of you just came by just now. Give me a minute, eh?
Okay, sir, it's okay.
Okay. Alright, so we move on. Alright, so the next thing is we call it as pitot tube. Alright, another part of our study in terms of Bernoulli equation application. And this one is a bit tricky because rather than using Bernoulli equation in terms of heat, we use Bernoulli equation in terms of pressure. Okay, so we have 2 types. Number 1 is more on experimental, meaning we have this apparatus over here. Flow is coming from left to right. Okay, and then we have one over here, piezometer, and then we have pitot tube. All right, so if you have a piezometer, doesn't matter which question that you see, piezometer is used to find static pressure. Right, and then pitot tube is used to find stagnation pressure. How do we find this? Through the height of the liquid inside the column or inside the tube. Right? So this is what we need to remember. Okay. And then other things from this is the height from your piezometer to the bottom is called H static. Okay. The height from your pitot tube location here to the bottom is called H stack. Okay. And then the height in between is called H dynamic. So if you want to find out what is the the height of H dynamic, what you do is you have to do this one, okay? This equation, right? If you see from my right side, please follow my yellow marker here, okay? So this is a way for you to find out how to calculate H dynamic. Okay, so by having H stagnation minus H static. All right, where does this come from? Okay, that comes from this equation here, which is P stagnation is equal to rho g H stagnation. P static is equal to rho g H static. P dynamic is equal to rho g H dynamic. Right, and based on that, we go for our Bernoulli equation over here in terms of pressure. And we cancel out things that we can cancel out from here. Okay, remember guys, whatever that I cancel out right now is not going to be the ultimate cancellation. Why? Because at this moment, Z1 and Z2 is the same elevation. We have to cancel out Z1 and Z2. If the question is not that way, okay, for example, the question is having the flow to be on sideways, okay, for example, maybe Z1 and Z2 is not at the same location. So Z1 and Z2 is available in the study, right? But for this one, for this picture, experimental setup here, Z1 and Z2 is at the same location. So we can cancel out, right? V2 equals to 0 because remember, stagnation velocity should equal to 0. If you ask me where is the stagnation then velocity, it should be at your L shape over here. Okay, right at the opening L shape. If you want to know whether a question is pitot tube or not, if you see an L shape, that will be a pitot tube. Sometimes L shape pitot tube will be on the front part, piezometer at the end. Sometimes like this, piezometer at the front, pitot tube at the end. It doesn't matter as long as which one is at the front or at the back, the velocity of V stack, which is the L shape, should equal to 0. Okay. Alright, so don't make it a habit. Oh, okay, as long as V2 is 0. No, the stagnation point will be 0. Meaning if the pitot tube is V1, V1 is 0. Right now the pitot tube is V2, so V2 is 0. Okay, so rho g z, everything. So when we cancel out, we get this equation here. P1 plus rho V1 square, this equation, over 2 equals to P2. P1 is what we call as P static. Rho V1 square over 2 is what we call as P dynamic. P2 is equal as P stagnation. Right? So there are 3 different ways to find out the velocity. So the function of pitot tube is to find the velocity or the speed of fluid, which is this one over here, V infinite that I show over here. Okay, so this is the velocity of fluid. Okay, so the way for you to calculate this is we rearrange this equation into number 1, where we have V1 equals to P2 minus P1 over rho, multiply by 2 and square root of everything. Right. The second way is, instead of using P2 and P1, we use the definition of P2 and P1. Okay, so remember, okay, based on the definition here, so let me write down over here. P rho GH stack is equal to P2, rho GH static is equal to P1, rho dynamic is equal to rho V1 square over 2. Okay, so instead of using P2, P1, we use in terms of P stagnation minus P static, and then we have P dynamic, okay, remember, and then we can just use rho GH dynamic. If you want to find out what is rho GH dynamic, you can use this equation. right? And we get the equation for V1 is equal to, so this is number 2 equation, 2 times G times H dynamic equals to V1. Right. And the last one, the third one over here, okay, instead of using this equation, you can just go with rho V1 square equals to rho GH dynamic. Also, both of them will provide you the same equation. So 3 ways for you to find out the velocity at point 1. Okay. Because velocity at point 1 should equal to the velocity of flow in the pipe. And the next one will be the pitot tube. Okay, this is pitot tube. For this question, for example, pitot tube plus manometer. Okay, so what happened here? For example, we have a manometer here. And then we have flow coming in from point 1 to point 2. So what we do here is, as usual, use Bernoulli equation to find out P1 minus P2. Use manometer to find out P1 minus P2. Okay, and then you compare. Okay, usually you do this as usual to solve an unknown. Okay, but normally when you do pitot tube to find out the velocity. Normally, velocity. Once again, any question?
I think not yet.
Tak ada, sir.
Not yet, at this moment, Alright, so this will be the last one for today, which is a study on linear momentum. Okay, so the study of linear momentum is a study of a question based on the idea of two different kinds, which is number 1, in pipe, number 2, outside the pipe, or we call it as jet. Alright, in pipe, it means that the flow is coming into a certain situation like this. Maybe we call this as an elbow, or sometimes we call it as bend, for example, or any nozzle, for example, will be a study of linear momentum. So what you need to do first is, each time you want to do the linear momentum question, you have the picture here, you add these two arrows. Okay, both on the inlet and both on the outlet. Okay, so for example, this is point number 1, this is point number 2. For the inlet, we have P1A1, m dot V1 coming in. P2A2 will always come into the pipe. Okay, m dot V2 will follow the flow. So remember, let me put it up here. PA goes into the pipe. Okay, and then m dot V, alright, follow the flow. Flow. Okay, so m dot V follows the flow. Direction. Okay, so P1A1 should be coming into, P2A2 should be coming into the pipe also. M dot V1 should go to the direction of flow. M dot V2 will also go to the direction of flow. Okay, so for this question, the flow is going that way. Right, so if the first thing to check is, if P at point 1, usually point 1 will be the main pressure inlet for the question, is not given, use continuity equation plus Bernoulli equation to solve for P1. So this is a very important part. We need to solve P1 first. Alright, and because this is in chapter 3, normally P1 will be in terms of gauge pressure. Okay, When you are done with getting P1, then you can do the linear momentum equation. So a continuation from this, before continuing with linear momentum, find P1 and P2. This is number 4 over here. All right. Sometimes this is atmosphere for point 2. Sometimes it connects to another pipe. So don't always assume P2A2 is equal to 0. You need to know whether this is continuing into a pipe or it is open to the atmosphere. All right. So first thing that you need to find out, V1 and V2, please make sure you find this out, usually through continuity. Right? And find out mass flow rate, okay? Because this will be used for our calculation. W, check whether it is available or not. If it's available, the equation will be M times G. Usually they give you in terms of mass. And P1 and P2 for the question. So next, to find out fx equals to 0, okay, to find out in terms of x direction, going to the right is positive, and this one going to the top is positive for y. Okay, first, check your P1A1. Right, so your P1A1 over here should be this way, horizontal to the right, so it's positive. Minus over here because of the direction. Okay, here positive because of the direction. Okay, and then check P2A2 is going to the left, so the direction is minus P2A2 cos theta because we have an angle here. Make sure check on the angle. Okay, plus FRX. So this one is fixed. I say it to you fixed because I don't want you to change to minus FRX or whatever. Just stick with plus FRX. Okay, equals to m dot v2 cos theta. So it's always this way. It's fixed. M dot v2, check over here to the right. So it's positive. So positive m dot v2. This is also direction. Cos theta due to angle. Minus, remember this is operation. Okay. It's always outlet minus inlet. Okay. For this part. So m dot v2 cos theta minus m dot v1. So this one based on the direction. Okay. So it's always outlet minus inlet. Why I separate the mass flow rate? Okay. Sometimes the question like this, mass flow rate will be the same. Sometimes when you have separation, remember we do a question on separation, the mass flow rate might be different. So that's why I separate this mass flow rate. If it's the same, you can do the factorization. Okay. And then if you check from FY, okay. So this is the example. Oh, everything is missing. Okay, it's okay. All right, it's coming back here again. Okay, so example, we have P1A1 minus P2A2 sine theta minus W. Okay, so P1A1 here. Why is it cancelled into 0? Because no y direction in the flow. Okay, so here P1A1, no y direction. Minus P2A2, why? Because P2A2 is coming down, so minus P2A2 sine theta. Minus WY, this one is fixed because your weight should always go downward, right? And then plus FRY, this is also fixed, okay? And then m dot v2 sine theta is positive here because of direction. M dot v1 is equal to 0 because there are no y direction in your study of m dot v1. Okay, so cancel out accordingly and then find the answer. So here Fr is equal to Frx square plus Fry square. So remember Fr is called as resultant force, okay, and then Frx, Fry. So this one is in term of x direction. This one is in term of y direction. Okay, all of this is called as anchoring force. Okay, if the question asks you find the anchoring force only, so you need to find the resultant force. If you have anchoring force in the x and y direction, you have to show separately. But in order for you to find Fr, you need to show Frx and Fry. So it means that to find Fr, everything should be done like this. And then you find Fr through this equation here. Frx squared plus Fry squared and square root of it, right? Angle of application, I put phi or theta, is just inverse tan Fry over Frx. Okay, it's good at the end you can show us the direction of force acting towards the system. Okay, any question on linear momentum?
No, sir. I think
No. Okay, so I think that will cover up everything in chapter 3. Okay.
Sir,
Yes.
A dengan M dot V tu sebenarnya equation dari mana?
M dot V. Wait, which one? Let me check on that. Which one that you say about?
Yang linear momentum.
Linear momentum. PA. Here.
PA.
Oh, okay. Sorry. Thank you for telling me that because we have outside the pipe question for jet. Let me tell about jet first, and then I will continue with where your PA and MV comes from. Is it okay?
Yes, sir.
Okay. So outside the pipe question about jet, okay, is what happens when you have water flows out from a pipe. For example, this is the pipe. Water flows from point 1 to point 2. Okay. So what happened? Both P0, P equals to 0 here. So all the P parts of the study, if it's jet, is equal to 0. Okay. So you will be calculating Frx and Fry in terms of m dot v only. Okay. Right. So a question about where do I come up with all this m dot v and PA? All right. Okay. Okay. Okay, so for this question, you are asking me where do I come up from PA? Okay, so the equation for force is, okay, force, all right, is equal to mass times acceleration. Okay, right, so usually you use force equals to MA, all right. So I've told you before in beginning of the class, MA, okay, means that you are multiplying mass with velocity divided by time, correct? Because A over here is in meter per second square, the unit. Alright, so it is equivalent to V over T, which is this one meter per second divided by second. So it becomes meter per second square, m dot v t, right? So if I bring the T on this side, mass divided by time, multiply by V, okay? So mass divided by time is actually mass flow rate. Okay, and the unit is kilogram per. So that's how the force becomes m dot v. Okay. the first part. The second part is pressure is equal to force multiplied by area. Okay, so P is equal to FA. So F is F divided by A. Let me right. So pressure is equal to force divided by area. Okay, so P is equal to F divided by A. So F is equal to P multiplied by A. Right, so anything that is on the pipe, we will talk about in terms of pressure. Okay, force coming from pressure and area. Anything regarding the flow of liquid, we will talk about momentum. So that's why in the calculation over here, I separate the calculation for pressure and I calculate the calculation for momentum so that you will get the idea on how to calculate pressure and also momentum differently, separately. Okay.
So that means PA and M dot V
Hmm.
represents the force coming in and out of the system lah.
Correct. So combination of P1A1 and M dot V1 will be the combination of force coming from your input. P2A2 and M dot V2 is the combination of force coming at the output.
Yes, sir.
Okay. Saya menjawab soalan ke?
Jawab sir.
Okay, thank you. Right, any other question?
So contohnya kalau water jet tu kan,
Water
so
jet.
kalau contohnya pressure tu equal to 0, so contohnya kita cari Fx, so Frx equal to M dot V2 minus M dot V1 tu je.
Correct. Yes. Kalau tak ada angle lah. If
So, sebab
your system have a separation, there is an angle there. So adalah sin theta or cos theta. If not, it's just the calculation of M dot V only. Because pressure for both sides is
okay.
0. Open to atmosphere.
Uh,
Okay. Ada question?